Principal of Rajiv Gandhi Memorial College of Engineering, Head of the Department of Civil Engineering, and also Dr. Rajaram. Thank you for inviting me. Just 1 second, I'm trying to share the screen. Is my screen visible?
Yes, sir. Yes, sir.
Yeah. So here today I would like to discuss about the 7th edition of IS 1893, which you all very well know that recently recently it was released. So what are the key changes in that, and then how to go forward? So these are the points which I would like to discuss. Yeah, so I will be touching upon the following things. One is what are the key changes in that, and what is seismic hazard, and what are the attributes of a good structural design, specifically with reference to 1893, and then what are the irregularities in a building, and if they are present, how to correct them, and then finally closing thoughts. So these are some of the things which I would like to discuss. So now coming to the notable events in India so far. Okay, so we know that Bihar-Nepal border, Uttarkashi, Latur, Jabalpur, and Chamoli, then Gujarat, Muzaffarnagar, that is Jammu Kashmir earthquake, all, and then Sikkim. So these are some of the recent earthquakes which occurred in the country and caused over 50,000 deaths, and around 5 lakh people got severely injured, and then 1 million buildings collapsed, and 5 million buildings suffered severe damage. So when it comes to reasons for collapse and damage to buildings, specifically we can attribute them to, first thing is unregulated development of built environment. So that is one critical or main reason. Then second one is large part of our country, buildings are self-built, so without any engineering intervention. And the third one is there is significant lack of awareness of earthquake standards and standards for design and construction. So these are the three key reasons. Now let's first understand what are the how the code has evolved and what are the current codal provisions for, especially for earthquake safety. So in the 7th edition, what are the key changes? There are 9 key changes in that. First one is the title got modified. The second is seismic hazard. Earlier it was deterministic, or maybe based on the epicenters. Now it is estimated probabilistically. Then the spectrum has been it has been increased up to the range of 10 seconds. Then another thing is acceleration coefficients are specified for zones, and then response history analysis with the real ground motion data. And there is a method which is given for the first time to how to account for the soil flexibility in the analysis and design. Then there was earlier liquefaction potential assessment method was present. It was improved method now. And next is this architectural elements and utilities. So which, when they are not secured properly, will cause severe injuries to occupants. And the 9th one is the code has become more modular. So that means what? The provisions are now given for RC buildings, masonry buildings, steel buildings separately as in the form of different parts. So overall, these are the 9 key changes. So we will not be able to address all of them today, but some of the points I would like to touch upon briefly on all these things and some in detail. Okay, I'm audible properly? Am I audible properly?
Yes, sir. Yes, sir.
Okay. Next, coming to the first one, what is the change in the title? So the earlier versions up to 6th version, it is criteria for earthquake resistant design of structures. Now it has been changed to design earthquake hazard, and criteria for earthquake resistant design of structures. And also it is given as a code of practice. So the first component, that is design earthquake hazard. So that means it is whatever is a given thing, we have to take that and use it for the design. Then coming to the second one, seismic hazard. So here I would like to give you a little brief. And I know that later after my lecture, Professor Raghukant, who has worked very hard for the new hazard map, so he will be giving more details on this one. But let me tell you that first seismic hazard map was formulated in 1962, and then the next hazard map immediately after 4 years after looking at the earthquake events map, that is, you can see zone 1 to zone 6 was there, that total 7 zones were there. So it was felt in next 4 years that the zone 1 portion has been reduced. Then after large number of earthquakes occurred from 1966 onwards up to 84, so number of zones were restricted to 5 only, zone 1 to zone 5. That was a revision in 1984. Then this was 5th revision. Then 6th revision in 2016, just 9 years back it came, and further it was reduced to 4 zones only. Zone 1, that means zone 1 is merged to zone 2 and some portions in zone 3. So that was the latest map in 2016. So till that time, all the hazard zonation map was based on the intensity, that means the impact of earthquake as well as where the epicenter is. So that was the basis for the zone map till 2025. And now 2025, after a lot of deliberations, maybe over 2 years, this map was discussed, and then finally this map is given. So this is now based on probabilistic earthquake hazard assessment. So in this one, this map gives, this is a 7th revision of the code. So this map gives only 5 zones as opposed to earlier 4 zones. So zone 6 got added. And if you can see the entire Himalayan belt, it is almost in zone 6 only. And then zone 5, some portion, zone 4, zone 3, and zone 2. This is a significant departure or change compared to the previous map. Now coming to how do we do this hazard assessment, that is probabilistic earthquake hazard assessment. In short, so first is sources, identify all the seismic sources. Second is find out the attenuation relationship, and then estimate the peak ground acceleration at the bedrock. That estimation is based on the probabilistic assessment. Then after that, bring that at the bedrock level by looking at the soil conditions, by using the scaling laws, that is scaled ground motion is taken. Then after that, shear wave propagation to the ground surface. So that's how we get PG at the ground surface. So this is the schematic map of the same process. So using this with tweaked in steps, the current hazard zonation map has been given. So that's what we are using now. So according to this map, if you look at, there are 5 zones. So zone 6 belongs to, the 21% of area belongs to zone 6, which may experience strong earthquake shaking. Then zone 5, 7%, which will experience severe ground shaking. Then zone 4, 9% high intensity ground shaking. And zone 3, 26% moderate intensity ground shaking. And 37, that is zone 2, low intensity ground shaking. Low intensity doesn't mean that there is no shaking. Definitely no part of the India is free from earthquake. So we have to design for this earthquake intensity. So as the code says that about 61% of land in India is prone to moderate to strong seismic hazard. Moderate to strong seismic hazard. Earlier, we used to say that moderate to severe earthquake hazard, but presently it is moderate to strong earthquake hazard. Now coming to the third important change, that is the design spectra. So design spectra is given for 2 methods. One is the static method, which we call it as equivalent static method, and then The second one is a dynamic method, which we call that as response spectrum method. In dynamic method, we have response spectrum method and response history method. So in these both, so long period structures are also taken into consideration, and the period is extended up to the spectra is extended up to 10 seconds, and it is given for 3 site classes. Actually, in fact, there are 5 site classes as per this 1893, but A and B are clubbed into one, C and D. So simply, how do we do, say, up to shear wave velocity value with which we define the ground, that is the site class, that is A, B, C, D, E. So E belongs to less than 180 meter per second. Then double of that, that is 360 to 180 to 360, that is class D, and then 360 to around 760 class C, and 760 to 1500 class B, and more than 1500, that is class A. That means hard soil, medium soil, soft soil. So these are the categories of that. So based on that, we have to select the spectra and get the normalized design horizontal elastic PSA, that is acceleration value. So now here acceleration coefficient values. So earlier we used to look at, say, zone factor, that is 0.1 for zone 2, 0.16 for zone 3, 0.24 for zone 4, and 0.36 for zone 5. So as opposed to that, the current one, the 2025 zone factor is elaborated. So this has taken importance factor also into consideration, and it is giving corresponding to the return period. So that means what, these return periods are used for what type of structure we are designing. Based on that, we have to select appropriate return period. So for all normal buildings, we select 475 years as a return period. So when we look at that, zone 2 value is 0.075 G, and zone 3 is 0.125 G, zone 4 is 0.233 G, and zone 5 0.333 G, and zone 6 0.5 G. So earlier the highest Z value what we used to take into consideration, that is 0.36 G. Now it has become 0.5 G. So let us not get confused with that suddenly zone factor values have been increased. So this is actually giving the clear picture of what earthquake hazard which country is facing in different parts. So as you can see here, normal structures are designed for 475 years return period. Important structures are designed for 975 years return period. Now you can see for 975 years return period, say in zone 6. So this factor is already taken into consideration, the what we call it as importance factor. And for critical structures 2475 and special structure 4975. So for very special structures like power plants and other dams, so it goes much beyond. So as you can see in the table, that is 9,975, approximately 10,000 years return period. So as you can see, if the return period is increasing, now acceleration coefficients are also increasing in this one, and also according to zone wise they are increasing. Then coming to dynamic analysis. So when it comes to dynamic analysis, as I said, we have response spectrum method and response history method. So when it comes to response history method, we need ground motions. So this code is a significant improvement now. So for zone 2 to zone 6, far field ground motion or far fault ground motions, 30 sets of ground motions are given, each in 3 directions, east, west, north, south, up, down. These are given. So 30 each for, say, zone 2, zone 3, zone 4, zone 5, and zone 6. And also for near fault ground motions, they are given only for zone 5 and zone 6, because the intensity of that ground motion in zone 2, 3, and 4 will not be that high. That is one reason. Second reason is we don't have recorded data in this, we don't have recorded data available so at present. So that's why maybe in future all these things may be populated. So the response history method is strengthened by providing suite of far fault ground motions for all the zones and near fault ground motions for zone 5 and zone 6. And also this envelope is to be the target design spectrum. It has to match with the target design spectrum. So this is quite evolved and detailed procedure is there. So maybe in the classroom when sometime teaching goes on, so your teachers will teach that. Then coming to modeling of soil flexibility. So when it comes to soil flexibility, earlier this was not there. So most of the cases, it used to be fixed soil, that is fixed base. So that means what, rigid base, that used to be considered, but now it is no more the case. So flexibility soil has to be considered for important, critical and special structures in all the zones. And then for all the structures resting on or in the site class C and D. As I told you, you can see that site class E means shear wave velocity less than 180 meters per second. Sorry, 180 meters per second. And then site class A means if the shear wave velocity is more than 1500 meters per second. So the structures in which the effects of geometric nonlinearity enhances stress resultants. That means what? Your P, V, M, and T. That means axial force, shear force, moment and twisting force. If they are increased by more than 15%, at that time also we have to consider soil flexibility. So what does soil flexibility means? You have to model the base not as fixed boundary condition, but as resting on the springs with this K vertical, that is the modulus of subgrade reaction, and K horizontal, that is, this is the modulus of subgrade reaction K. So this is a independent or individual footing or isolated footing, pile foundation and well foundation. So for all these categories, we have to take the soil flexibility into consideration. Then coming to method of liquefaction potential assessment. As like simple formula, so factor of safety against liquefaction is the ratio of that critical, that is cyclic resistance ratio by cyclic stress ratio or critical stress ratio. So the equations are given here. So they are almost the same with minor tweaking in the formula. CSR formula is given, that is mainly based on the what is the acceleration value in that zone under consideration. This has been given by Seed and Idris, and CRR value is linked to soil conditions, that means resistance, how much it will resist. The standard value is given for magnitude 7.5 earthquake, and based on what magnitude and what intensity we are designing, this magnitude scaling factor will be used. So that is the method for liquefaction assessment, potential assessment. And then the new clauses were introduced, that is architecture elements and utilities. See, people will die when building collapse, but sometimes what happens is building has not collapsed, but there are a lot of items which are electrical elements as well, sorry, architecture elements as well as utilities. So like TV, refrigerator, AC, and some wall hangings, and then some buildings have a lot of other elements, and if it comes to hospitals, a lot of non-structural elements will be there. So these will cause severe injury, and also at the same time they will disrupt the function of the building. So especially hospital is needed immediately after the post-earthquake activity. So that kind of buildings definitely need, and also these days houses have a lot of non-structural elements. So for that, these clauses are there. So they are subdivided into acceleration sensitive AEUs, deformation sensitive AEUs, and acceleration cum deformation, that is combined. So when acceleration sensitive AEUs are there, they are usually stiff and massive. They will slide or topple. So we have to protect them. Then deformation sensitive AEUs, that is they are flexible and long, which move and move or swing. So we have to protect them so that functional requirement is continued. So these clauses are also present. This is the 8th significant change. Now coming to the 9th significant change. So earlier the buildings, clauses related to buildings were in part 1 itself. Now they have been divided, they have been separated. So part 1 gives some general provisions, and after that reinforced concrete buildings, that is in part 5, and then masonry buildings and steel building, they are all in part 5. So these are given in part 5. Now coming to design earthquake hazard. Am I audible?
Yes, sir.
Yes, sir.
Okay. So this is design base shear, horizontal design base shear formula. As you know, acceleration coefficient multiplied by seismic weight. So if you can notice the change in the formula, earlier it used to be Z by 2, I by R, SA by G multiplied by W, seismic weight. Now the formula has been changed. Okay. And also Z factor, that is zone factor. As I told you, zone factor is now dependent on the return period. So return period is selected based on what type of structure you are constructing. So based on the structure type, return period is selected. Based on return period, we get Z value. So that is one thing. Importance value for all types of buildings is taken as 1. So for part 5, that is for buildings, in that I is 1. So that means that Z in Z value that is subsumed. And now response reduction factor depending on the type of structural system we are selecting. And now coming to acceleration coefficient, which is dependent on the natural period in principal plan direction. So this is the main formula, and then W is the seismic weight. Now coming to two methods. First one is equivalent static method, that is static method. So this is given for site classes. As you have seen, there are 3 curves in the design spectrum. So for site classes A and B, so that means what? Site classes A and B, it is given, that is hard soil basically. So the formula is given in 3 ranges. One is up to 0.4 seconds, that is 2.5, and from 0.4 seconds up to 6 seconds, and then 6 seconds to 10 seconds. Coming to site class C, again it is extended up to 0.6 seconds because of the flexibility, and then for site class D up to 0.8 seconds, that is 2.5. So this is acceleration coefficient value dependent on natural period to be used in the base shear formula. Then coming to the response spectrum method, which is dynamic method. So these values have given, that is site classes A and B. So if you are doing like dynamic analysis, that is response spectrum analysis, the values are given. These are again, this is that curve, that is a design spectrum curve, which is if you want to code it, you can use this formula. Then coming to similar formula are there for vertical base shear also. So this is horizontal, and then vertical base shear also, similar formula is there. Now coming to criteria of earthquake resistant design. So there are 4 main attributes for earthquake resistant design. So what are the 4 things? First one is robust structural configuration is needed. Second one is at least minimum initial elastic lateral stiffness, that is a K value. Then second is the third one is overall strength. So what is the minimum allowable overall strength? And then the fourth one is adequate ductility. Ductility means even after structure has crossed the yield limit, how much of it can sustain. So that is toughness. So these are the 4 main attributes. So because of the paucity of time, I'm planning to cover the first one in detail. So let's look at structural configuration. So mainly what code specifies is, in each principal plan direction, there should be at least 2 lateral force resisting planes should be available. So that is very, very important. If they are not available and are not of the same strength, then twisting of the building might happen, and load which is induced seismic force, which will be usually generated at the level of a diaphragm, that will not be taken properly to the base. So that is the main idea behind 2 lateral force resisting planes shall be provided in each principal plan direction of the building. So this is the intent of structural configuration. So when the structural configuration is very simple, then this kind of thing is possible. If the structural configuration itself is complex, then providing 2 planes, it will be very, very difficult, and structure goes into lot of adverse effects, so which I'm going to discuss because of the irregularities. So what structure is called regular and which structure is called irregular. So that is clearly been defined in clause 7.1.3 in the new code. So what it says is buildings with simple regular geometry and uniformly distributed mass and stiffness in plan and in elevation suffer much less damage than irregular configuration buildings. So for the purpose of the code, what does it indicate? What is the meaning of irregular configuration? That I am going to discuss from little while now. So you can see whenever irregular configuration is there, what code is saying is limits are put on irregularities for seismic zones 3, 4, 5, and special requirements are laid out actually for 3, 4, 5, and 6 also. So the irregularities in earlier version, they were given in table 5 and 6. Now they have been clubbed in one table here, one table. So what is that? What this table clearly signifies is, so irregularities are of different types. There are 5 types. One is geometry irregularity, mass irregularity, stiffness irregularity, strength irregularity, and behavior-wise irregularity. So these are the 5 categories in which these are clubbed. And in addition to that, these irregularities are defined in plan as well as in elevation. So when you look at this in plan, we have re-entrant corners, mass irregularity that is there both in plan and elevation. So like that, and behavior-wise irregularity. So this is the total building-wise, that means total envelope. So torsional flexibility, flexible floor diaphragm, closely spaced modes, and irregular modes of oscillation. So these are behavior-wise irregularities. Now let's go and look at one by one. So plan irregularity, we call that as re-entrant corner, which is given in 7.1 clause, 7.1.3 actually. So you can see here, what simply it indicates, if the projection is more than 15% of overall dimension in that direction or in principal plan direction. So that is the definition. So structural system in plan has a projection of size greater than 15%. So if that is there, what will be the problem if such kind of irregularity is there? What happens is there will be poor earthquake performance. What does it mean, poor earthquake performance? That means stress concentration will take place at the junctions here. So what is needed? Solution is 3-dimensional analysis shall be performed. So that is the solution. So problem and reason for problem and what is the solution. So in this format, I will explain all these things. What is the meaning of irregularity? What are the adverse effects due to that irregularity? And what is the solution suggested by the code? Then coming to vertical geometric irregularity. As you can see, if say building is tapering like that, and if the portion which is irregularity is more than 20% of the dimension in that principal plan direction, so then it is accounted for irregularity, all these kind of things. So what do we do if such irregularity is there? So if such irregularity is there, again we need to perform dynamic analysis, and drift limits are limited. So this is vertical geometric irregularity. Then coming to mass irregularity. So what mass irregularity, how can we say that there is an irregularity of mass? So what happens is, if so the mass of the floor, any floor, is more than 1.5 times of mass above, okay, or below, then that goes to mass irregularity. So when mass irregularity is there, again what code is suggesting is we have to perform dynamic analysis and find out what kind of forces are acting on the structure or acting on the lateral load resisting system, which has to be designed for. Then coming to stiffness irregularity. Stiffness irregularity in plan. So in stiffness irregularity in plan, what it is saying is, first one is non-parallel lateral force resisting systems. So something like this. So non-parallel. So if the lateral load resisting systems, which are say moment resisting frame as well as structural walls, if they are not aligned parallelly in principal plan direction, then we have to use a certain load combination, which is force in one direction plus 30% of force in other direction to be added to one principal plan direction and perform dynamic analysis, and whatever forces or stress resultants are coming as an outcome, that should be taken for design. So that is the extra effort we need to do when frames are not parallel or lateral load resisting systems are not parallel. Then coming to again another stiffness irregularity, there are 3 stiffness irregularities in plan. So first one is non-parallel frames. The second one is in-plane stiffness discontinuity. So that means what? The induced earthquake force is generated at the slab level, that is the diaphragm level, which is called diaphragm level. So diaphragm will feed the force, that means from diaphragm, lateral load resisting element, that is vertical lateral load resisting elements will take it as a feed and then take it to the base, that is a support, wherever support is there. But if that diaphragm itself is becoming flexible, then the distribution will not be proportion to the stiffness. So that is the problem. And the 2 definitions are given here. One is if the cutout area is more than 25%, if the cutout is not at the edge, and if the cutout is at the edge, if it is more than 10%, then we should consider it as there is a discontinuity. So the cutout definition is already given. So that is less than 15% of the dimension in the principal plan direction. So that is that. Then what to do in such situation if discontinuity is encountered? Then perform dynamic analysis with flexible floor diaphragm as an assumption. So then distribution will not be related to or in proportion to lateral stiffness, but it will be related to the flexibility. So then higher forces will be there and force distribution will be different in different lateral load resisting elements. So this is next one. Then coming to the third plan irregularity, which is related to stiffness, that is out of plane offsets in vertical elements. As you can see here, the partial be offset. So that means what? These frames, when you look at partial and full, they are offset in plan. So when they are offset in plan, what code says? This kind of offset is not permitted in zone 3, zone 4, zone 5 and zone 6. They are allowed, if they are coming in the plan, they are allowed in zone 2 only. And that too, code places a severe restriction, that is forces have to be increased by overstrength factor, and also drift has to be restricted by 0.2% of that story height. So this is a stringent clause. It is going to change the way we design. Then next one is coming to soft story. So the definition of soft story is same. There is no change in the definition from the earlier code. What it says is soft story definition simple. If any story's stiffness, that is lateral stiffness, is 70% of the floor above or less than 80% of the average of 3 floors above, then we declare it as a soft story. That story is soft story. So what code says? It is not permitted. This kind of soft story is not permitted in 3, 4 and 5. 3, 4, 5 and 6. And then if at all it is present in zone 2, which is a less earthquake hazard prone area, then what it says is 2 things. One is perform dynamic analysis. Second is drift is restricted in that floor as well as all the floors below to 0.2% of that floor height. Then coming to in-plane discontinuity in vertical elements. As you can see, this is in-plane discontinuity. Earlier one was out-of-plane discontinuity. This is in-plane discontinuity. So when in-plane discontinuity, when we say that if the offset is less than, more than 20% of in-plane. So as you can see, structural wall. So there are a lot of restrictions in that. Number one, it is not permitted in 3, 4, 5 and 6 zones. Second is in zone 2, drift of that story is limited to 0.2, and then design with irregular distribution of forces, and offset is not permitted more than 50%. So that is another severe restriction in stiffness irregularity. Then coming to floating columns. So these floating columns you must have seen in many buildings, in a lot of apartments, floating columns. So these floating columns are not permitted if they are carrying more than 10% of the design lateral force. So that lateral load resisting element, if it is carrying more than 10% of the overall design base shear, then it is not permitted. So it is permitted only if it is carrying less than 10% of the design lateral force. Then coming to weak story, that is irregularity in elevation, weak story. So weak story definition is also given if, say, the story lateral shear strength of the story is less than that of the story above. So if it is less, then what it says, it is not permitted in 4, 5 and 6 zones. In zone 2 and 3, members below up to foundation shall be designed for all additional forces. Okay, and then another thing is this weak story definition has to account for that URM, that is unreinforced masonry infills. So that provisions have to be followed. Then coming to behavior, that is torsional flexibility. So torsional flexibility, what code says is, when do we say torsional flexibility is there? If the torsional mode is higher than translational mode, then it is said to be having torsional flexibility. So building with torsional flexibility, clearly code says that it is not permitted. Okay, and what we have to do, we have to change the configuration such that it falls into that category. Yeah, so center of mass, center of resistance, I am skipping this one for the paucity of time. Yeah, torsional irregularity, as you can see, it's simple example. So when building mass is evenly distributed, center of mass usually falls in the on the center. Then, as you can see here, stiffnesses on x-axis they are not uniform. On y-axis they are uniform. So then what happens is center of resistance is shifted towards the higher stiff elements. So that means in this building, during shaking, twisting will take place. Okay, so how the twisting will take place? From center of resistance, center of mass will twist towards center of resistance. So that means clockwise twisting. So in the second case, it is anti-clockwise twisting. So here that both are there. So eccentricity along x-axis, eccentricity along y-axis, both are there. So it will building will have a complex structural behavior. Then coming to behavior-wise, flexible floor diaphragm. So when we declare a floor to be flexible floor diaphragm, as you can see, when the building under the action of seismic force is deforming, so there are two edges. One is delta minimum and delta maximum. Average is average of both, that is delta minimum plus delta maximum by 2. So if the mid axis or mid portion deformation is 20% more than average, then we call it as flexible floor diaphragm. That is the definition. Now, if such case arises, what do we do? So it is divided into two components. One is 20% to 40%. Up to 20% to 40%, what code says is perform dynamic analysis. That is three-dimensional dynamic analysis by taking into consideration in-plane flexibility of the floor. And if it is more than 40%, that is 1.4 times average, then structural configuration has to be revised such that it falls in category number 1. Then closely spaced modes. So when do we call this as closely spaced modes? If the difference between first mode and the second mode, or any two modes, fall within 10% of the higher mode. So in two principal plan directions. So then we call it as closely spaced modes. Okay. So, and then buildings with irregular modes of oscillation also has similar definition. Here what it says is, if say first three modes contribute less than 65% of mass participation, then it falls in the category of irregular modes of oscillations. So in seismic zones 4, 5 and 6, it shall be ensured that the 65% mass contribution from first three translational modes should fall within. So otherwise we have to do the correction and make it fall in that range. Okay, so finally I would like to end with some closing thoughts. So as I said, 3 reasons. One is unregulated development. Second one is individual houses are largely self-built. And the third one is lack of awareness of earthquake standards for design and construction. So basically we have addressed the part number 3, that is the 3, what are the current or the latest code provisions which came into force recently. So we have to understand and sincerely use the code for design of structures which resist earthquake forces. So finally, I would like to acknowledge that is Rajiv Gandhi Memorial College of Engineering, Andhra Pradesh, Nandyal, and Professor Rajaram, and then all the BIS Code Committee members, that is CD 39 members, especially the chairman, Professor C.V.R. Murthy, the chairman of the committee, and my students and colleagues who have worked hard, and then finally some. Thank you very much.
Thank you, sir, for giving the wonderful lecture on overview of IS 1893-2025, the latest revisions. Any questions from participant side to the speaker? Yeah. Yeah, you can unmute and ask questions.
Sir, good morning, sir. My name is Dr. B. Santosh Kumar, working as a Deputy Executive Engineer, Irrigation Department of Andhra Pradesh, sir. So, for first two question is that, is there any commentary book or elaboratory book is to be adopted or releasing, sir? First thing,
No,
and at the same time,
at present it is not there. Maybe some people are going to work on that, but it is not there at present.
Okay, sir. Sir, second one is the IS 456 also be revised. That is, the draft code has been released just now, sir. Even though January it is released, recently it was released. Is there any compatibility? Because I attended your session on in the 2019 at the GVP College. CVR Murthy sir and you and all the other things are coming and giving the lecture. But at the same time, that draft was released just now. But is there any compatibility for our 1893 and other codes, sir?
Yes, they are compatible, and that code, that CED2 IS 456 is almost at the finishing stage. So BIS will maybe release it soon.
Sir, sir, is there that is the dynamic analysis? Is there any software, sir? We have to use the SAP or ETABS?
Yeah.
It
Actually,
has to be modified.
after the release of the code, see, analysis methodology is same, but the codes have to adopt with the new changes in the code. So that is, softwares have to adopt with the new changes in the code, which will happen soon, very soon.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.
Any further questions?
Good morning. May I ask?
Yes. Carry on, Ankit ji.
Good morning. This is Professor Ankit Asher from Sardar Patel College of Engineering, Mumbai. Thank you, Pradeep sir, for giving such a wonderful presentation. Sir, I have one doubt about the 3D dynamic analysis for buildings with plan and vertical irregularities. So
Okay.
code says it has to be 3D dynamic analysis. Is a response spectrum analysis sufficient for that, or compulsorily it has to be a time history analysis?
No. Response, as the case may be, response spectrum analysis is fine.
Okay. And sir, one question about response reduction factors. So over the years, IS code has not changed any values of response reduction